4 August 1943. At Bovington Camp in Dorset, a damp morning haze hung low over the parade ground as Major General A.C. Richardson drafted a highly classified report stamped "Most Secret." His notes outlined the start of a large-scale reliability trial, one that would quietly confront a painful reality for Britain's armored forces. 3 different national tank designs were about to undertake a 2,000-mile endurance journey across the United Kingdom. By the end, only one approach to tank building would justify itself under sustained operational strain. 11 vehicles idled in formation that morning, their engines revealing distinct mechanical personalities. 3 American-built M4A2 Shermans, fitted with General Motors twin diesel engines, ran with a steady, controlled rhythm. Alongside them were 3 M4A4 Shermans, powered by Chrysler's multi-bank petrol engines, equally consistent in tone. Britain's entries included 3 Cromwell Mark I cruiser tanks, equipped with the new Rolls-Royce Meteor engine, powerful but not entirely smooth in operation. 2 improved Cromwell Mark III models joined them. Completing the lineup were 3 Centaur Mark I tanks, still reliant on the aging Liberty engine, which had already shown its limitations in earlier cruiser designs. Their uneven, strained engine notes hinted at trouble before the test even began. The crews had no sense that this exercise, later known as Exercise Dracula, would become one of the clearest wartime comparisons of armored vehicle reliability. During the cross-country trial would challenge British assumptions and influence tank procurement policy for the remainder of the war. The conclusions would also echo in post-war military planning, shaping how democratic nations evaluated the balance between performance and reliability in weapons development. The roots of this reassessment lay far from England. In the North African desert campaigns of 1942 and early 1943, British cruiser tanks operating in extreme heat and abrasive sand had developed a troubling reputation for mechanical breakdowns at critical moments. The Crusader tank, capable on paper of reaching 26 miles per hour and theoretically offering a mobility advantage, too often sat immobilized along desert tracks instead of advancing toward enemy lines. The Liberty engines that powered many British cruisers suffered from persistent oil leaks. Cooling systems designed for temperate climates failed under desert temperatures that could push interior tank conditions beyond 130 degrees Fahrenheit. Gearboxes cracked under sustained strain, suspensions fractured over rough terrain, and electrical systems faltered amid dust and sand. Crews adapted by carrying substantial spare parts and accepting that breakdowns were part of routine operations. The cost was lost mobility, reduced combat availability, and declining morale. Meanwhile, American M4 Shermans supplied through the Lend-Lease program began arriving in increasing numbers. Senior British commanders took note. General Bernard Montgomery, leading British forces in North Africa and later in Northwest Europe, privately acknowledged that American tanks could be trusted to function consistently, whereas many domestic designs remained unpredictable. In London, the War Office confronted an uncomfortable truth. Years of engineering experience and significant industrial investment had produced several cruiser tank models that failed to meet wartime demands. The Covenanter, introduced in 1941 with high expectations, proved so mechanically unreliable, particularly due to chronic cooling failures, that it never entered combat service, despite more than 1,700 units being built. The Crusader that followed saw action but continued to experience persistent mechanical shortcomings. The Cavalier, initially linked to early Cromwell development, retained the flawed Liberty engine and was soon relegated to training duties after tests confirmed no meaningful improvement in reliability. Britain urgently required a cruiser tank that combined performance with sustained operational endurance. A promising solution emerged from Rolls-Royce, a company renowned for luxury automobiles and increasingly prominent in aircraft engine production. Engineer W.A. Robotham and his team adapted the celebrated Merlin aero engine, famous for powering the Spitfire and Hurricane fighters during the Battle of Britain, into a ground-based power plant known as the Meteor. This V12 engine produced roughly 600 horsepower and was expected to deliver both high performance and improved durability. Promise would withstand extended operational testing was precisely what Exercise Dracula set out to determine. Initial trials of the new British cruiser tank produced results that surprised even its supporters. On proving grounds, the Cromwell pushed past 40 miles per hour, an extraordinary figure for a wartime tank. That performance made it the fastest British armored vehicle of the conflict, and among the quickest fielded by any nation. Full-scale manufacturing began in January 1943. Factories across Britain's industrial centres prepared for output. Companies such as Leyland Motors, Birmingham Railway Carriage and Wagon Company, Metro Camel, and English Electric adapted their production lines for the new tank. The hope was clear. This vehicle would finally counter German armored strength and reduce Britain's reliance on foreign designs. By mid-1943, Cromwells were leaving assembly lines in significant numbers. Plans were drafted to outfit entire armored divisions with the type. For the first time in years, British formations might deploy a domestically produced cruiser tank, combining high speed, a 75mm gun compatible with Allied ammunition stocks, respectable armor, and, so it was hoped, mechanical dependability. Yet concerns emerged almost immediately from units that received early production models for training. Reports described oil seepage around the engine compartment, posing both fire risks and the possibility of visible trails detectable from the air. Brake systems sometimes faltered during prolonged use, particularly on descents. The pressing question was unavoidable. If problems surfaced in peacetime-style trials, how would the tanks perform during sustained combat operations far from workshops and depots? Before committing to the Cromwell as Britain's principal cruiser tank, the War Office sought clear evidence. In July 1943, senior commanders authorized a large-scale endurance evaluation. The new British tanks would be measured directly against American-built Shermans that had already seen action in North Africa, Sicily, and Italy following the Allied landings. The exercise, known as Exercise Dracula, would involve a 2,000-mile journey across varied British terrain, designed to replicate the strain of an extended campaign. Roads, dirt tracks, and cross-country routes were included, along with exposure to the damp and unpredictable conditions of a British autumn. Maintenance was to be conducted strictly under field conditions. Crews could use only standard tools and procedures outlined in service manuals. No factory specialists, no specialized civilian support. The objective was straightforward: determine whether the Cromwell was fit for frontline deployment or required further refinement, at a time when delays carried strategic costs. To guarantee impartiality, organizers imposed strict controls. All vehicles were standard production tanks taken directly from factory output, not specially prepared prototypes. Crews consisted of experienced British personnel trained on both domestic and American equipment, minimizing bias due to familiarity. Each vehicle followed identical routes and encountered the same operational challenges. Every malfunction, however minor, was recorded. Multi-bank engine, essentially 5 automotive engines integrated into one power unit. Both variants had already proven themselves in active theaters. Crews who had transitioned from British designs to Shermans frequently expressed confidence in the American machines. Representing Britain's newest engineering effort were the Cromwell Mark I and Mark III, powered by the Meteor engine derived from the Merlin aircraft engine. Their 75mm guns fired the same ammunition as the Sherman, simplifying logistics. For comparison, the Centaur Mark I, fitted with the older Liberty engine that had underperformed in previous designs, served as a benchmark, illustrating the technological gap the Cromwell was meant to close. The first 10 days of the exercise was spent at Bovington Camp, the Army's principal armor training center. Mechanics thoroughly inspected each vehicle, correcting pre-existing faults to ensure a fair starting point. Crews familiarized themselves with their assigned tanks, noting individual characteristics. Detailed documentation procedures were established so that subsequent data could be measured against a carefully recorded baseline. As preparations progressed, rivalry between crews became increasingly evident. Many British tankers were eager for their domestically designed vehicle to outperform its American counterpart, validating years of national development. Those assigned to Shermans, particularly veterans who had operated them in combat overseas, displayed a quieter assurance, confidence grounded in battlefield experience rather than expectation. The exercise was designed to push machines and crews alike. Each day combined long highway marches with cross-country travel over farmland and open ground, followed by tactical drills meant to replicate the strain of combat. Weather would not be controlled. British late summer conditions offered rain, mud, cold evenings, and occasional clear skies. Every night, maintenance teams performed inspections at designated halts, recording every malfunction in detailed logs compiled by observers traveling with the formation. Mechanical trouble surfaced almost immediately. Before the first 10 miles had passed, one Centaur began emitting smoke from its engine bay. Its aging Liberty engine showed signs of strain under continuous use. By the evening stop north of London, the same vehicle was leaking oil badly enough to require 2 hours of urgent repairs. Elsewhere on the column's route, a Cromwell experienced severe brake fade while descending a long hill, forcing its driver to rely on low gears to slow the tank safely. The Sherman tanks, in contrast, reached the first halt without incident beyond standard servicing. Their crews carried out routine evening checks and prepared for the next day's advance. Observers continued documenting every detail, gradually building a dataset that would reveal unmistakable trends. After the first week, patterns were clear. Centaur tanks regularly arrived last at the nightly stops, sometimes hours behind schedule. Crews were exhausted from coaxing failing vehicles forward. Persistent oil leaks from the Liberty engines left stains along the roads and caused chronic pressure problems. Among Centaur crews gave way to a grim determination to avoid being withdrawn from the trial altogether. Cromwell tanks performed noticeably better than the Centaurs, but still fell short of expectations. Oil seepage around engine seals demanded constant attention. Brake systems proved insufficient for a vehicle capable of 40 miles per hour, with dangerous fading occurring on long descents. As the exercise progressed, clutch failures became more frequent. Mechanics attributed these issues to designs that could not fully handle the torque of the Meteor engine. Steering difficulties persisted during rough cross-country movement despite prior modifications. Most troubling to senior officers reviewing interim reports was the fact that these deficiencies were not new discoveries. Many had been identified during earlier testing but remained unresolved when production began. Sherman tanks displayed a different pattern altogether. They started reliably each morning, a seemingly minor detail that British crews did not take for granted. March speeds were maintained without drama. When repairs were necessary, they were predictable and manageable rather than disruptive emergencies. The diesel-powered M4A2 variant demonstrated exceptional durability, with one experienced crew remarking that its engine seemed almost immune to breakdown under sustained use. The more complex multi-bank M4A4 required slightly more attention, but still surpassed British tanks in overall dependability. The American emphasis on mechanical simplicity and operational reliability, favoring consistent function over ambitious performance figures. In practice, breakdowns often delayed 1 or 2 tanks until late at night. The result was missed meals, reduced rest, fuel convoys held idle, and guides waiting for hours in cold darkness. Mechanical failure affected not just individual crews, but the rhythm and morale of the entire unit. By early September, as the formation neared completion of its circuit, the compiled statistics underscored the disparity between designs. Every defect and every hour of maintenance had been recorded and assembled into detailed tables for a restricted final report circulated among senior military and political leaders. The 3 Sherman M4A2 tanks collectively traveled 13,986 miles, exceeding the planned distance, while sustaining 199 recorded defects, an average of 66 per vehicle. Across all 3, specialist mechanics devoted 420 hours to maintenance, or roughly 140 hours per tank. This equated to approximately 0.03 maintenance hours per mile, about 2 minutes of servicing for each mile traveled. For armored vehicles operating under field conditions far from factory support, this level of reliability was remarkable. The 3 Sherman M4A4 tanks showed somewhat higher maintenance demands due to their more intricate multi-bank engines. Yet their overall performance remained close to that of the diesel variants. Official assessments grouped all 6 American tanks together as clear examples of superior reliability. The contrast with British machines was stark. When required, the data from the trial made the contrast unmistakable. For every mile traveled, the Cromwell demanded roughly 0.07 hours of servicing time, more than twice what was required for the American Sherman over the same distance. In practical terms, that meant over 4 minutes of maintenance per mile for a Cromwell, compared to about 2 minutes for a Sherman. On paper, the gap between 0.07 and 0.07 hours might appear trivial. In the field, it was decisive. Units equipped with Shermans could keep moving while Cromwell crews were still under the hull, tools in hand. The Centaur's performance was even more troubling. Across the exercise, the 3 Centaur tanks together managed just 8,492 miles, repeatedly sidelined by mechanical failures that left them immobile for long stretches. They accumulated 297 recorded defects and consumed 742 maintenance hours, almost matching the Cromwell's total repair time, despite covering far less ground. Their average of roughly 0.087 hours of servicing per mile placed them close to 3 times the Sherman's requirement. In every measurable category, the Centaur lagged behind. Its Liberty engine, an aging design, proved incapable of sustaining the demands of modern armored warfare. The vehicle had remained in production, largely to keep factories active while output of the Meteor engine expanded. The trial confirmed what critics had long argued. The Centaur represented a costly misallocation of precious industrial capacity. The numbers reinforced his point. A commander equipped with Shermans could reasonably expect 99% of his tanks to be battle-ready during their first 2,000 miles of service. By comparison, officers relying on Cromwells or Centaurs would operate under constant uncertainty, unsure how many vehicles would survive the march to the front line. Even more damaging was the context. The exercise had been conducted under conditions favorable to the machines. Although long distances were covered, units consistently reached harbor in time to perform maintenance during daylight hours, with adequate facilities and support. Despite these advantages, British tanks remained operational only through extraordinary effort by crews and mechanics. In active combat, where time, spare parts, and workshop space were scarce, performance would almost certainly deteriorate further. This concern was echoed by Alec Richardson of the British Tank Mission, who had observed American evaluations of British vehicles in late 1943. His private assessment was blunt. The repeated mechanical troubles of the Cromwell, he noted, had undermined confidence. American officials responded not with sharp criticism, but with cool detachment, a reaction he found equally troubling. Even representatives from Rolls-Royce were reportedly eager to withdraw the vehicles to avoid further embarrassment. Richardson concluded that Britain's armored vehicles could not be sent abroad again until they were genuinely competitive. Restoring the nation's engineering reputation would require patience and a commitment to getting the design right, however long that might take. Confined cooling environments, the adaptation was never seamless. Oil seals suited to aviation leaked under the pressure patterns of armored use. Cooling arrangements that worked flawlessly in open air struggled within the cramped hull. The engine looked exceptional on technical drawings. In operational reality, it revealed its compromises. Other weaknesses reflected rushed development. The Merritt-Brown gearbox offered refined handling and flexibility, but introduced complexity and additional failure points absent in simpler American transmissions. Brakes proved inadequate for a 40-mile-per-hour vehicle, leading to dangerous fade on prolonged descents. The clutch lacked the durability to manage the Meteor's torque output. Suspension components, derived from earlier cruiser designs, were strained by increased weight and higher speeds. Individually, each subsystem had passed controlled testing. Under sustained operational stress, their vulnerabilities surfaced. At the heart of the matter lay a broader divergence in design philosophy. British engineers had prioritized speed and firepower, assuming that skilled maintenance crews could compensate for mechanical fragility. That assumption held in peacetime environments, supported by established depots and abundant spare parts. Wartime realities, extended operations, stretched supply lines, and relentless tempo exposed its flaws. American designers, by contrast, accepted moderate performance in exchange for consistent function. When subjected to realistic field conditions, this approach proved more effective. Implementing these changes required months of coordinated adjustments across multiple production facilities. The finalized specification for what Leyland Motors termed the Battle Cromwell was not settled until February 2, 1944, incorporating both sweeping reliability improvements and numerous smaller refinements. Only then did the vehicle approach the operational dependability that modern mechanized warfare demanded. In November 1943, a new and far more rigorous series of trials revealed that the revised Cromwell tank had improved substantially over the problematic models tested in August. Engineers had addressed many earlier weaknesses, and the upgraded vehicles performed noticeably better. Even so, they still failed to equal the dependability standards set by the American M4 Sherman across every category. The Centaur tank, however, told a different story. Despite repeated attempts to refine it, performance gains were negligible. Its Liberty engine simply did not generate enough power for the vehicle's weight, a structural limitation no mechanical adjustment could fix. As a result, the Centaur was largely abandoned as a frontline fighting vehicle. Many were reassigned to training duties, where mechanical unreliability posed fewer risks, or converted into specialist machines. Armored recovery vehicles, artillery observation platforms, and engineering variants, such as the turretless Centaur dozer, fitted with a bulldozer blade. By June 1944, the Cromwell entered combat service, equipping reconnaissance regiments within British and Polish formations during Operation Overlord. Armed with the same 75mm gun used by the Sherman and firing identical ammunition for logistical efficiency, the Cromwell possessed adequate firepower against most German armored vehicles. Still, it struggled against the heavy armor of Tigers and Panthers. Its tactical strength lay in mobility and discretion, avoiding drawn-out duels where its thinner armor and limited penetration became liabilities. The broader implications of Exercise Dracula extended well beyond comparative tank trials. The tests underscored a fundamental military principle: reliability is not a luxury, but a decisive operational asset. A vehicle that cannot consistently reach the battlefield is strategically irrelevant, regardless of its theoretical performance. A moderately capable tank that functions predictably will outperform a technically superior machine prone to breakdown. American designers grasped this concept from the outset. British engineers, long accustomed to pursuing peak technical performance, were forced to absorb this lesson after the public embarrassment of the trials. The Sherman that outclassed the Cromwell in those evaluations was hardly flawless. Its armor could not reliably withstand high-velocity fire from German Panther or Tiger tanks. The 75mm gun lacked the penetration needed against heavy armor at range. Crews grimly nicknamed it Ronson after the cigarette lighter brand, implying it ignited too easily when hit. Polish soldiers referred to it as a burning grave. These were not minor shortcomings, they cost lives. Yet the Sherman remained in mass production and continuous frontline service because it worked. They were transported overseas aboard Liberty ship vessels, maintained in the field by ordinary crews, and replaced quickly when lost. Damaged vehicles were often repaired and returned to service within a day. This integration of manufacturing, logistics, and field maintenance proved more decisive than advanced engineering refinements. Production figures highlight contrasting industrial philosophies. Germany manufactured roughly 6,000 Panther tanks, and about 1,300 Tiger I tanks during the war. On paper, these designs surpassed the Sherman in armor protection and firepower. In practice, they were over-engineered, slow to produce, and demanding to maintain. Complex components required specialized manufacturing facilities and highly trained mechanics. Mechanical failures were frequent during extended operations. Had a German armored division attempted the kind of rapid 400-mile advance across France achieved by Allied forces in 1944, many of its vehicles would likely have succumbed to breakdown long before reaching their objective. Post-war experience reinforced this reality. The French army experimented with captured Panthers, but found them impractical and unreliable compared to Lend-Lease Shermans, which remained in French service into the 1950s. The Soviet Union received more than 7,000 Shermans through Lend-Lease and developed an unexpected appreciation for them. Observed that damaged Shermans left unattended were quickly stripped for spare parts by other Soviet crews, an informal but telling endorsement of their value. This reliability translated directly into operational tempo. Sherman-equipped divisions could sustain prolonged advances, not because they were the fastest vehicles on paper, but because they remained functional day after day. Covering 40 miles daily over extended periods was realistic with minimal mechanical attrition. German formations attempting similar advances often lost more tanks to breakdown than to enemy fire, steadily eroding their strength. By 1944, after years of relentless campaigning, German equipment was increasingly worn and overstretched. Allied armored units, benefiting from superior mechanical uptime, could exploit breakthroughs, maintain momentum, and keep opponents under continuous pressure. The cumulative effect proved decisive. Historian David Fletcher, long associated with the Tank Museum, summarized the Sherman's defining virtue succinctly: it would start each morning and run all day. This dependable, unspectacular consistency made it indispensable. British crews may have admired the Cromwell's speed or coveted the Firefly's powerful 17-pounder gun, but they trusted the standard Sherman to function without fail. American tankers openly criticized its vulnerabilities against German heavy armor, yet they rarely doubted its mechanical loyalty. Reliability lacked drama, but it determined outcomes. Armored forces that arrive at the decisive point intact and ready to fight will outperform those immobilized by their own machinery. Altogether, production of the A-27 family amounted to just over 4,000 vehicles, including roughly 950 Centaur variants and about 3,000 Cromwells. By comparison, American factories produced more than 49,000 Shermans. The contrast was not merely numerical, it exposed the strategic imbalance between British and American industrial strength during the war. Britain's manufacturing base was stretched across competing demands. Shipyards were turning out vessels for the Royal Navy, aircraft plants were feeding the Royal Air Force, and factories were supplying equipment to multiple theaters around the globe. Under such strain, armored vehicle production could not approach American output. As a result, the Cromwell was not fielded in vast numbers, but was instead assigned primarily to reconnaissance formations within British and Polish armored divisions. Units where mobility and speed were valued more than heavy armor or long-term mechanical endurance. Several prominent formations relied on the Cromwell in these specialized roles. The 7th Armored Division, celebrated as the Desert Rats for its North African service, used the tank extensively for scouting missions. The 11th Armored Division incorporated Cromwell-equipped reconnaissance elements that capitalized on its rapid movement. The Guards Armored Division deployed it effectively in screening and flanking tasks, while the 1st Polish Armored Division handled the vehicle with notable skill during operations in northwest Europe. In these forward reconnaissance assignments, the Cromwell's strengths were clearer: enemy movements without being detected. When circumstances permitted, they maneuvered against the flanks or rear of heavier German tanks, targeting weaker armor sections where the 75mm gun could still be effective. The Cromwell thus found its place not as a breakthrough tank, but as a fast and agile scout. Following the end of the war in Europe in May 1945, the Cromwell remained in British service into the 1950s. Reflecting improvements introduced after reliability shortcomings had been exposed during earlier large-scale trials. It even returned to combat during the Korean War, where British units such as the 7th Royal Tank Regiment and the 8th King, His Royal Irish Hussars, operated it alongside the newer Centurion tank, which was gradually entering service. Beyond Britain, the Cromwell was exported to several nations rebuilding their armed forces after 1945, including Australia, Austria, Finland, Israel, and Jordan. Some hulls were later converted into the Charioteer tank destroyer by fitting a more powerful 20-pounder gun, serving as an interim solution until Centurions became widely available. The vehicle that had once drawn criticism for mechanical fragility ultimately achieved a respectable post-war career, demonstrating that targeted refinements could significantly improve operational reliability. Meanwhile, the Sherman established an even broader legacy. It fought across North Africa, Italy, Northwest Europe, the Pacific, and China during the Second World War. After 1945, it remained in service with numerous armies. In Korea, Shermans proved capable against Soviet-supplied T-34-85s. Modified Shermans took part in the Six-Day War and the Yom Kippur War, underscoring the adaptability of the original design decades after its debut. Remarkably, Shermans remained in Chilean service until 2003, over 60 years after production began, making the Type 1 one of the longest-serving tanks in modern military history. The broader lessons drawn from large-scale wartime trials extended well beyond this single-vehicle comparison. They highlighted a principle that would echo through post-war procurement debates: theoretical performance figures are meaningless if machinery cannot function consistently under field conditions. Pursuing technical sophistication at the expense of durability and ease of maintenance can undermine battlefield effectiveness. Equipment that can be produced in large numbers, maintained with limited resources, and kept operational by ordinary crews often proves more valuable than smaller quantities of advanced but temperamental systems. These conclusions also illuminated the widening industrial gap between the United States and Britain by the mid-war years. American industry had refined mass production techniques, building on earlier innovations in automotive assembly and large public works programs, into a system capable of turning out standardized, reliable machines at extraordinary scale. Quality control, interchangeable components, and assembly line efficiency allowed U.S. factories to deliver not only quantity but consistency. Britain, constrained by older facilities and competing demands, struggled to match that output. Ultimately, the experience reinforced a truth understood most clearly by the soldiers themselves. War reliability was not a secondary virtue, it was the foundation upon which battlefield success depended. During wartime field operations, tank crews quickly formed opinions about the machines they depended on. Units assigned vehicles that frequently failed in the middle of maneuvers developed a cautious, almost fatalistic mindset. Mechanical breakdowns did more than slow movement, they eroded trust. When soldiers doubted their tank would function at a decisive moment, they hesitated, avoided calculated risks, and fought defensively. By contrast, crews who believed in the dependability of their vehicles acted with greater boldness. Confidence in machinery translated directly into aggression and tactical initiative. This psychological dimension became unmistakably clear during Exercise Dracula, a large-scale British trial conducted in 1943 to measure the sustained performance of different cruiser tanks. The exercise demonstrated with measurable evidence that reliability influenced morale and combat output in ways that went far beyond maintenance logs. A trusted tank produced cohesive, assertive crews who focused on the enemy. An unreliable one generated anxiety, soldiers worried more about mechanical failure than hostile fire. The final classified report, submitted in late September 1943, circulated among Britain's highest military and political authorities, including Winston Churchill. Its conclusions forced senior leaders to confront uncomfortable truths. Years of investment in domestic tank programs had not delivered the operational dependability required for sustained warfare. The findings would shape British procurement decisions for the remainder of the conflict. Rather than rapidly replacing American-supplied M4 Sherman tanks with the domestically produced Cromwell tank, Britain would continue to rely primarily on Shermans, while improvements to British designs continued. The numerical results were stark. The Sherman required approximately 0.03 hours of maintenance for every mile traveled. The Cromwell demanded around 0.07 hours per mile, more than twice as much. The Centaur tank performed worse still, at roughly 0.087 hours per mile. These figures were not abstract statistics. They translated directly into battlefield capability. A formation equipped with Shermans could travel farther in a day, spend more time ready for combat, and sustain operations with less interruption. Units using Cromwells or Centaurs lost significant operational tempo to repairs. The trial exposed a fundamental contrast in engineering philosophy. On paper, the Cromwell appeared impressive, higher speed and competitive firepower within similar protective limits. In controlled specifications, it looked superior. In prolonged realistic field conditions, however, it spent far more time immobilized for maintenance. The assumption that advanced performance characteristics would automatically confer advantage proved misleading. The decisive factor in extended campaigns was not peak speed or technical sophistication, but mechanical endurance under stress. The 2,000-mile endurance test removed ambiguity, underestimating the importance of sustained dependability. The outcome can be small fleets of extraordinarily complex, expensive platforms that demand intensive maintenance and struggle to match the consistent performance of simpler systems. For the soldiers who participated, the trial reshaped personal convictions. Sherman crews felt confirmed in their long-standing preference for American-built machines. Cromwell crews advocated vigorously for mechanical revisions that would make their vehicles viable in real combat. Crews assigned to Centaurs reacted with relief upon learning their tanks would not face German armor directly. Major General Richardson's concluding assessment in the final report summarized the issue with clarity. A commander equipped with Shermans could expect nearly all of his tanks, about 99%, to reach the battlefield during their first 2,000 miles of service. A commander relying on Cromwells or Centaurs, by contrast, would operate under constant uncertainty about how many vehicles would arrive ready to fight. That disparity explained why British armored divisions continued to depend heavily on American tanks even after improved domestic models became theoretically available. Subsequent modifications eventually transformed the Cromwell into a competent vehicle for reconnaissance roles. Its reliability improved to acceptable levels for sustained operations, though it never fully equaled Sherman standards across all measures. In its specialized function, rapid exploitation and scouting, it performed effectively, yet it did not replace the Sherman as Britain's principal cruiser tank. American manufacturers emphasized mass production, strict standardization, and reliability engineering as foundational principles. British industry, shaped by long-standing craft traditions, often prioritized refined performance and technical excellence within individual units. In the unforgiving environment of mechanized warfare, the American emphasis on robust simplicity proved decisive. Exercise Dracula ultimately illustrated a recurring truth of military technology. Theoretical superiority on paper does not guarantee operational success. In sustained combat, the machine that keeps running is the one that wins. In civilian markets, British manufacturers traditionally excelled at producing refined, high-end goods that justified premium prices. Their craftsmanship and engineering sophistication were widely admired, yet when the context shifted from peaceful commerce to the brutal realities of mechanized warfare, a different standard applied. On the battlefield, elegance and advanced specifications meant little if machines failed under pressure. In that unforgiving environment, American industrial philosophy demonstrated a decisive advantage. The contrast became unmistakable during Exercise Dracula, one of the most significant yet often overlooked comparative trials of the Second World War. The test placed major Allied cruiser tank designs under controlled but operationally realistic conditions. Rather than relying on theoretical data or short demonstration runs, the trial subjected the vehicles to sustained use across 2,000 miles of demanding terrain. Breakdowns, the Sherman kept moving. A third design, the Centaur tank, fared worst and was eventually reassigned to training and specialized roles. The implications were immediate. British authorities were compelled to confront systemic weaknesses in their tank development process. The Cromwell, in its August 1943 configuration, was simply not ready for large-scale front-line deployment. Correcting its shortcomings would demand time-consuming modifications and production adjustments. Meanwhile, the Sherman had already proven itself in combat in North Africa, Sicily, and Italy. It had endured real war, not just controlled trials. For British commanders, the decision was less about national pride than operational necessity. The choice was between a domestically produced tank that showed promise but broke down too often, and an imported vehicle that consistently worked. The comprehensive data gathered during the trial removed ambiguity. Reliability, not theoretical capability, would determine effectiveness in Northwest Europe. Looking back more than 8 decades later, the lessons remain strikingly relevant. The trial underscored the importance of evaluating weapons under authentic operational conditions rather than depending solely on laboratory metrics or promotional specifications. It demonstrated that engineering for durability and maintainability, deserves at least as much priority as maximizing peak performance. It also highlighted how industrial culture influences military outcomes. A philosophy centered on standardization, simplicity, and mass production can outperform one focused on refinement and technical sophistication. The Sherman that completed 2,000 miles with relatively limited servicing went on to fight across the European continent. The Cromwell, after undergoing extensive redesign and improvement, eventually became serviceable, but only after months of corrective effort. The Centaur, unable to meet expectations, was relegated away from primary combat roles. These divergent trajectories were not primarily the result of crew competence or designer intent. They were the product of mechanical dependability under stress. At its core, the trial answered a pressing strategic question: could the Cromwell replace the Sherman as Britain's principal cruiser tank? The evidence-driven conclusion was clear. Replacement was premature until substantial reliability improvements were achieved. That determination influenced British armored policy for the remainder of the war and shaped post-war development thinking for years to come. There is a deeper irony in this episode. Britain had long been synonymous with industrial innovation and engineering excellence, having pioneered much of the 19th century Industrial Revolution and contributed critical wartime technologies such as radar and early jet propulsion. Yet, in the specific domain of mass-produced armored vehicles, American industry's emphasis on ruggedness, standardization, and production efficiency produced a more battle-worthy machine. Ultimately, the trial was about more than 3 tank models. It represented a contest between 2 engineering cultures. One prized technical sophistication and finely tuned performance. The other prioritized functional reliability and streamlined production.